Sound in the real world is a continuously varying wave, analog, taking any value at any instant. A computer cannot store that because it would need infinitely many values. So it samples. It measures the wave's amplitude at regular intervals and records each measurement as a binary number. Notice this is the same problem as the sensors in topic 3.2 and the same solution, an analog to digital converter doing the measuring. And notice what sampling necessarily loses. Between two samples, the wave did something and none of it was recorded. The digital version is an approximation built from measurements, and how good an approximation depends entirely on the two settings in this lesson. The first setting is the sample rate, the number of samples taken per second measured in hertz. CD quality is 44,100 hertz. 44,100 measurements every second. A higher sample rate means measurements are taken closer together, so the digital version follows the original wave more faithfully, and higher frequencies are captured accurately. A lower rate means gaps between measurements, and detail falling into those gaps is simply lost. Think of it as how often you look at the wave, and the analogy that fits is frames in a film. Too few, and the motion becomes jerky because you did not look often enough to catch it. The second setting is the sample resolution, also called bit depth, the number of bits used to store each individual sample. CD quality is 16 bits per sample, giving 2 to the 16, 65,536 possible amplitude values. A higher resolution means each measurement can be recorded more precisely, so quiet detail survives and the sound is more accurate. A lower resolution means each measurement is rounded to a coarser value, which introduces distortion. So keep the two apart because this is what the exam tests. Sample rate is how often you measure. Sample resolution is how precisely you record each measurement. One is about time, the other about accuracy. Now the calculation, which has three factors rather than the images too. File size equals the sample rate times the sample resolution times the duration in seconds. Take 1 second of CD quality mono audio, 44,100 Hz, 16 bits, 1 second. 44,100 times 16 is 705,600 bits per second. Divide by 8 for bytes, 88,200 bytes. Divide by 1,024 for kilobytes, about 86.1 kilobytes for a single second. Now the two things that scale it up. Stereo means two channels left and right, so multiply by 2, about 172 kilobytes per second. And a 3-minute song is 180 seconds, so 172 times 180 gives roughly 31,000 kilobytes, which is about 30 megabytes. 30 megabytes for one uncompressed song, and that number is worth sitting with because it explains the entire existence of the next lesson. An MP3 of that same song is 3 or 4 megabytes, roughly a tenth, and compression is what makes carrying music around possible at all. The impact table, read as trade-offs. Increasing the sample rate improves quality, particularly for high frequencies, and increases the file size proportionally. Increasing the sample resolution improves accuracy and dynamic range and increases the file size proportionally. Decreasing either reduces both quality and size. And because the formula multiplies, halving the sample rate halves the file, but halving both the rate and the resolution quarters it. That multiplication is the thing to notice. These settings compound rather than add. If a question asks what happens to the file size when the sample rate is doubled and the resolution is doubled, the answer is 4 times, not twice. And playback, which completes the circle. The stored samples are binary numbers, and a speaker needs a varying electrical signal. So a digital to analog converter reads the samples and reconstructs a continuously varying voltage from them. That signal is amplified and drives the speaker, whose cone vibrates and produces sound waves, exactly as we covered in topic 3.2. So the full chain is sound wave, microphone, analog signal, ADC, binary samples, storage, and then back the other way, samples, DAC, analog signal, amplifier, speaker, sound wave. The ADC and DAC sit at the two ends, and every digital audio system you have ever used has both. 4 things to take into the exam. First, the formula has 3 factors: sample rate times, sample resolution times duration, and forgetting the duration is the commonest error because the image formula only had 2. Second, if the audio is stereo, multiply by 2 and say that you have done so. Third, keep the 2 settings distinct. Sample rate is samples per second. Sample resolution is bits per sample. Defining one when asked about the other is a wasted answer. And fourth, watch the units all the way through. The formula gives bits. Questions usually want kilobytes or megabytes, and every division needs to be shown. These are method mark questions, so the working is worth more than the final number. And one comparison worth carrying, because it puts the 3 media types in order. A page of text is about 3 kilobytes. A photograph is a few megabytes, roughly 1,000 times more. And 1 minute of uncompressed CD audio is about 10 megabytes, so a few minutes of sound outweighs a photograph. Text is astonishingly cheap, images are expensive, and uncompressed audio is more expensive still. That ordering explains a great deal about how the internet developed. Text moved freely on slow connections decades before images did, and streaming audio and video had to wait for both faster networks and better compression.